So let's start the recording, please. Okay, so hello everyone, welcome to this week's AI seminar. Today I'm very happy to introduce Dr. Chenguang from Microsoft. So Chenguang is a principal research manager in Microsoft Cognitive Services Research Group, where he leads the knowledge and language team. So his research covers knowledge-enhanced language modeling, text summarization, and future learning. Dr. Zhu has led teams to achieve human parity in CommonsenseQA, highlights where COCA and the first places in CommonGen, Fever, ARC, and Squad. So all are very challenging tasks. So Chenguang holds a PhD degree in computer science from Stanford University. So today, he's going to talk about how they achieved human parity in CommonsenseQA based on fusing knowledge into language models.
Thanks a lot, Mohao, and great thanks for the invitation organization. So I'm really glad to be here. So I'm Chenguang Zhu from Microsoft Cognitive Services Research. Today, I'm going to talk about how we achieved human parity in CommonsenseQA, specifically how to fuse knowledge into language models. Now, this is joint work with a lot of great collaborators, as shown here, from both Microsoft and then also a lot of universities. So if we look at the recent development of NLP models, we notice there is a clear trend of developing larger and larger models. And they are becoming so huge that even for like big tech companies, very few of them can afford the pre-training cost. And even if they can afford it, it comes with a huge environmental impact. And if you say, okay, I cannot afford the pre-training, I just use it to fine-tune on my small data set. But that is even impossible for a majority of researchers and practitioners. For instance, for the GPT-3, if you want to host it and fine-tune it locally on your machine, for that 175 billion parameter model, you need at least 24 V100 GPUs, which is a daunting task to start with. On one hand, we notice that with the increasing size of models, the performance generally tends to become better. But the question is, does model size solve everything? In other words, if we just keep increasing the model size to 10x, 100x, 1000x, and so on, can we reach human parity intelligence in this way alone? Based on various researches in this field and also our experience, the answer is unfortunately probably no. There's still a sizable gap between what these models output and how humans output. So we can still notice that models make mysterious or sometimes silly errors here and there. But then the question is, why are we still doing it? Investing more and more money into this endless larger model competition. To answer this question, I would like to draw an analogy where a man lost his key in a park at night, and he tried to look for it in the park. But instead of searching for the key in the whole park, he just focused on the small circular area illuminated by the lamppost. After an hour, a friend of this man came and asked, have you found it? The man answered, no. And the friend said, then why do you just search for the key in this area, not like in the whole park? The man answered, because here is the only place where I can see anything. So if we consider the key as the human level intelligence, then this small circular area is what we can do. Like we can invest more and more money to build larger models, but that does not necessarily bring us closer to the human level intelligence. Right. So in this talk, I'm going to propose some alternative routes that may potentially bring us closer to our ultimate goal. We call this external attention to knowledge. So knowledge is not a new topic in NLP. Actually, if we take a look at NLP, the central topic is called language model, or LM. Its goal is to learn how to express as naturally as humans do. And after training on billions of sentences written by humans, it is not hard for a language model to know that I go to school to want is an ungrammatical sentence, while I want to go to school is a correct one. But learning how to express is just one part of human language intelligence. The other big part is what to express, and knowledge usually helps. For instance, to answer this question, where is the painting Mona Lisa? The language model tells us we should start the answer with the 3 words it is in. But what to fill after these 3 words comes from some external information not present in this question. As humans, we know Mona Lisa is a famous painting currently stored in Louvre, Paris. So the full answer should be it is in Louvre, Paris. Some people may argue that a language model can also learn knowledge. While a large language model can learn knowledge and facts to some degree, according to some papers, it is highly inefficient. For instance, it may take tens of sentences, including Mona Lisa is in Louvre, Paris, to make a language model implicitly embed this information. However, several nodes and edges in the knowledge graph, like shown here, can precisely confer the same information. Thus, resorting to external knowledge can be made more efficient. With that, we revisit the language models, like those huge ones, like GPT-3. What they try to do is to memorize everything it sees during its pre-training, including the language patterns, facts, knowledge, etc., inside its parameter space. This is also part of the reason why large language models appear to perform better, since they memorize more. But instead, we propose to use a decent-sized language model with basic language understanding capability, like how to express. And then, when it carries out a task, it leverages the vast amount of external knowledge, which has unlimited size, is constantly updated, and is explicitly understandable by human beings. The knowledge can be stored in various formats, not just in knowledge graphs that we are most familiar with, but also, say, in dictionaries as definitions, in free text like in Wikipedia, or from other language models' output. So here we refer to knowledge as any external information absent from the input, but helpful for generating the output. In summary, the language model can delegate the task of memorizing knowledge from its own parameter space to external sources, which are usually non-parameterized, making the whole process much more efficient and effective. Definitely, this is always easier said than done. So how can we both effectively and efficiently integrate knowledge into language models? Based on our work and investigation into related literature, we summarize that there are 3 key steps. First, we need to ground language into related knowledge. Second, we need to represent that knowledge. And finally, we have to fuse that knowledge representation into a language model. Let's get into the details. In the first step, we need to ground the input text into related knowledge. The reason being that for a specific question, definitely we don't need all the pieces of information from the vast knowledge source. Instead, we only require the related knowledge. So this step is called grounding. We can leverage techniques as simple as string matching, or a little bit more complex, say named entity recognition, anti-linking, or use information retrieval. So the goal is to identify concepts and relations in the input that are also in the knowledge source. Then for the second step, since knowledge are stored in various sources, we need to represent it in some uniform way so that the downstream language model can understand. We can either store it in text format, say concept names, like using its canonical names from the knowledge graph, or the description, like the definition from the dictionary. Or we can represent it in non-text way, usually in a numerical vector we call embedding. For instance, we can compute the graph embeddings using graph neural network on the knowledge graph, and then return the node embedding corresponding to the entity or concept appearing in the text as the representation of knowledge. Finally, how to fuse that representation into language model depends on how we represent it. If we represent the knowledge as text, we can just simply concatenate it with the input. If it's like represented in embeddings, we can either append or add the embeddings to the word embeddings. Like the pen, it has the word embedding, but also it has the graph embedding from the knowledge graph. So we can either append or add. Or we can make it a little bit more involved using attention. So attention is a mechanism where the model during its computation can dynamically determine how much weight, how much emphasis can put to various parts of the external information. Like in the first layer of the transformer, it can put more weight on the node embedding for the first concept. Maybe in the second layer, it will put more weight on the red one. So it will decide by itself to make the output more accurate. So to summarize here, there are 3 steps: the grounding, the representation, and fusing. So in the rest of my talk, I will introduce 3 of our recent works where we have followed these 3 steps to integrate knowledge into language models for various tasks. The first one is the CommonsenseQA. CommonsenseQA is a multiple choice task about common sense knowledge. So for instance, an example question from the training set is, where would I not want a fox? And the correct answer from these 5 choices is hen house. Thus, as humans, we know to answer this question, we need to know 2 facts. First, fox eats hens. Second, we don't want to lose hens. Thus, we don't want a fox near the hen house. But for models, if it wants to answer this question correctly, it cannot just look at the inputting question, because this question contains little clue of what the correct answer is. You need more information beyond that, like those common sense. That's the hard part of this task. But if you say, okay, I just want to use an existing language model on this task, and let's see the result. So definitely we can. So the basic model is, we have the language model here. We concatenate the question with each choice. And then we use the embedding on the CLS token to generate a numerical score, which is the confidence score that the language model thinks that this choice is the correct one. So let's see how it performs. It turns out that, yes, if you use more advanced language models, the performance can increase. But to reach human parity, there is still about 4% behind it. And like we tried using even fancier language models and didn't improve upon this 86.7. So notice that even the largest pre-trained model, like the GB3 we tried, actually got a pretty poor score. Probably because, like you say, the data set is not large enough, or it's actually beyond the knowledge learned inside its parameters, because it has not seen these before. So let's start the journey of integrating knowledge. The first question we want to answer is what knowledge we want to use. We first turn to knowledge graph. Because CommonsenseQA, this data set is special, is constructed from a knowledge graph called ConceptNet. This is a large-scale knowledge graph about concepts and the relations between them. For instance, here it says wake up in the morning is a prerequisite of eating breakfast. So remember, the first step of leveraging knowledge for LM is grounding. Fortunately, for this dataset, CommonsenseQA, that is for free. It provides the entity in the ConceptNet, gives the link to it called EQ, and then for the choice entity, it gives as EC. So we try to see whether there is a relation between them. If there is one, we just concatenate all the names, the relations, and these 2 entities together as the textual representation of the knowledge. Finally, we fuse it by just like appending it. So for instance, if the question is where is Mona Lisa, choice is Louvre, and CSQA datasets gives the entity names, and we found that, okay, there is a is-in relation, then the full input to the model would be CLS token, question, choice, followed by a separator. then question entity separator, the choice entity separator, and then the triple, including the relation. So very interestingly, this can already improve the accuracy a lot by nearly 7%. Although we are still not at human parity yet. So the key here is that this new information, the relation, actually says a lot about the answer. And the language model alone does not acquire most of that. Otherwise, these two accuracies would be similar. So let's move on with more knowledge. The second source of knowledge we found is relatively non-traditional for deep learning, but as humans, we use that a lot. This is called dictionary. The reason we look to dictionary is its unbiasedness towards the frequency of words. If we look at the pre-trained models, they are inevitably more familiar with common words and less so with rare or new words. Because in the pre-training data, some simple words, commonly used words, will just appear more. So the models will have more times to train for those words, but less so for those rare words. But dictionary can provide precise definition from those linguists to key entities, irrespective of its frequency. They will always get an entry there. So what we do is we found the concepts, like entities, in the input question and choice, and look up a definition from Wiktionary, which is an online version of dictionary. If we find it, we just append that information to the input. So here again, we use textual representation. Thus, back to this example, other than the KG information here, we also find the definition for Mona Lisa and Louvre, like here. Say Mona Lisa has an entry in the dictionary says a painting by Leonardo da Vinci. So append that just after the question entity name. We notice that there's 3 points more improvement in the development accuracy. Although we are still we're closer to the human parity. So to finish the final gap, we look to a very non-traditional source of knowledge, training data, which people rarely thought of. In machine learning, we know that in the traditional model training, we train the model on input X in the training data, and then get the answer Y. And then we compare it to the ground truth answer in the training set and update the model if it's incorrect. Usually, what we think is that after training the model on the training set, we can essentially throw away the training set because the model has seen that. It's supposed to remember everything from the training data. Actually, various methods has been proposed to limit the model's capability of just memorizing. This phenomenon is called overfitting. So people use regularization and other dropout stuff to limit that capability. But we argue that even after training, the model cannot memorize everything. So we did this experiment. For every input X, we retrieve similar inputs to that X inside the training data using information retrieval to get, say, the top 5 or top 10 training data instances pairs. So get X1 corresponding Y1, X2, Y2, and etc. Then we just append these pairs with the input and send that to the model to get this Y. The intuition is that just like when you are working on an exam, you are allowed to look at your previous homework, exercise problems, and then you find a problem that is similar, then you read its answers. So it should help. If the model can memorize everything from the training data, then what we do here will have no help because this is just redundant information. But it turns out that the model cannot. So according to our experiments on various NLP tasks, summarization, machine translation, language modeling, etc., adding this retrieval from the training data actually helps, and it helps a lot. So that proves that the model actually cannot remember everything in the training data, and it helps to provide it with similar training data. Actually, here we notice a interesting phenomenon. Like for the smaller model, like BART base, after adding the retrieval from the training data, it can sometimes even surpass the performance of BART large, which is about 3 times larger than it. So this is what we want. Like we want to use external knowledge from various sources, in this case, training data, to like decrease our dependence on the model size. We don't need such a large model. We can just use a smaller model and coupled with knowledge. So with that, with the KG information, with the dictionary as a knowledge source, and then with the training data as a knowledge source, we actually improved the performance a lot to 89.8. Definitely, to use this retrieval from a training data technique, we don't need to confine ourselves just to the training data of CSQA. We actually look at like more related tasks, more common sense reasoning tasks, just like you have more exercise books and homeworks from other schools to refer to. And it turns out it adds us 1 more points for single models. After we ensemble all the models, we get a result over the human parity for the first time for the CommonsenseQA. So it's actually 0.5% higher than human parity. So this is what we call KEER model, or knowledgeable external attention for common sense reasoning. Okay, so any questions so far?
Yes, there are a couple of questions. So one question is from Joe. My understanding is that the question is about, let's say, when you retrieve the triplets from the concept net and append it in the context of MCQA, do you apply that in your fine-tuning stage, or do you just apply that in the inference stage?
Both. So all of the techniques, including dictionary, including this triple, and also the training data retrieval, are all applied in both fine-tuning and inference.
Mm-hmm. I think Zihao asked one question. So do you have an example of those X and Y's in RENA? I'm not sure if you have that in the slide.
That's a good question. I can just talk about example here. So for example, the X here is where's Mona Lisa, right? And then X1 is a similar question from the data set. Say, where are all the paintings of Da Vinci, or like what is the current storage place for Mona Lisa, for example. And then the corresponding ground truth label is Paris, or Louvre, Paris.
Okay, yeah, thanks. So another question is about basically this work you are showing. So what if there's no data, no relevant enough data to augment from the retrieval process? I guess the question would be, do you have any way to measure the uncertainty so the model knows that there's no suitable reference data to retrieve?
That's a good question. I think that is related to the new scenario of say few-shot learning or even zero-shot learning. First, we can have some people just label a minimum amount of say 100 pairs. That will help a lot. Another way is we don't need to just focus on this task. As shown in the CommonsenseQA task, we can actually retrieve from related data sets if of the similar types, and then it will also help.
Okay, so these are all the questions we have so far. Thanks.
So move on. So for the CSQA human parity work, it's English only, but there are many languages in the world. How can we let multilingual models benefit from knowledge, common sense reasoning, like from those knowledge integration? Unfortunately, we find that most of the knowledge sources are in a few languages, especially in English. Here is a distribution of the languages for the definitions in Wiktionary. We find that, okay, English has a predominant distribution here. So other languages have like much fewer definitions. So how can we let multilingual models also enjoy from that? That is our work, related work for this. And we use a very simple trick called translate, retrieve, and translate. So given an input from other languages, we first translate it into English and then retrieve the knowledge in the English knowledge sources, which is vast, and then translate the knowledge text back into the original source language, and then do concatenate. So this is what we call TRT. In this work, we also systematically look at the benefits from various knowledge sources. We have seen dictionaries, we have seen knowledge graph, but in this work, we also look at free text and also other big language models output, because we know large language models contain some knowledge there. So we try to elicit them from them. Here is an example. Given a question and answer choices in foreign languages, we first translate it into English. And then for each of the knowledge source, we conduct the grounding, representation, and fusing. So for instance, for the dictionary definitions we have done before, just use string matching to find the words, say in the choice or in the question, and then get that definition. For knowledge graph, we use entity linking. Like this time, for this data set, they don't provide like free NER, so we just do it ourselves. So the representation is the canonical name of the entity in the knowledge graph, and then the neighboring node, and also their relation. For free text, naturally, people think of information retrieval, so we use BM25 as a retriever to get related sentences from a Commonsense text corpus called OMCS. So the output is some sentence related to the question or choice here. And finally, we also prompt the GPT-3 model to get its interpretation of certain entities. For example, here, the prompt is, how is riding a bike getting it to move? Answer is pedaling. And then we say pedaling, colon. So we let GPT-3 to output its interpretation, explanation of the word pedaling. Definitely, we give it a few examples before to let it know what this task is. And then no matter what the output is, it's a source, is some text, and in English, we translate it back into foreign language and concatenate it with the question and candidate answer, and use the cross-lingual model to generate the score for that choice. We conduct experiments for each of these sources. You can guess like which knowledge source proves to be most useful for this data set. It turns out to be a dictionary. So for the CXQA and XCODA, for these two different settings, 3 out of 4 times Wiktionary got the best improvement. On the other hand, most, like all of the additional knowledge gain performance here. So notice that the baseline is 55.1 and 57.4. So all of them like improve the performance. So this is our method of applying knowledge for multilingual language. Maybe there are also like other works that can make the multilingual knowledge like easier to adopt. So this is also an open question. So that wraps up the first thread of work, the CommonsenseQA. Second, let's look at DictBird. So we already know that dictionaries are very helpful. And in this task, we try to answer whether we can use knowledge, in this case, dictionary, also in pre-training. Because previously, one audience asked whether we use it in fine-tuning or inference. So we use it in fine-tuning and also inference, but not in pre-training. So what if we also use knowledge in pre-training? So this slide says, okay, dictionaries are helpful. It provides definitions for new words and rare words, as we know. In this work, we use BERT as the base language model and make modifications to it by adding dictionary information. Recall that in BERT, the most important pre-training task is called mask language model, where you mask certain words and try to use the contextual embeddings to predict what word was masked. So here we first adopt that MLM learning objective, but notice here we append the definitions of those masked words from the dictionary here, separated by SCP. We also optionally put in some negative words, negative definitions, meaning this words actually did not appear in the original text. It's not masked, but this word is related to the masked words in some sense, says in the thesaurus is similar. We just let the model to be more aware of the negative information. So the first loss is the MLM. And the only difference from BERT is that we append more stuff to the end. The second loss is that because we know for this definition, it defines the word masked here. So their representation in these two vectors should be similar. And we'll try to maximize the mutual information between these two vectors. However, maximizing the mutual information between two high-dimensional vectors is infeasible. So we use a feasible lower bound called NCE, which is basically try to correct. We can just construct positive samples and positive pairs between this X and C, and negative pairs between this X prime and C. We try to increase the similarity between the two vectors, between the positive pair compared with those negative pairs. So this is the loss. And thirdly, since we inserted those negative definitions, we just have a binary task to tell whether this definition defines a word masked in this input or not. So for example, this one should be right because COVID was masked here. Epidemic is right, but the SARS was not. So this it should output 0 here. So that wraps up our losses defined in the pre-training phases. Then during fine-tuning, we also append the definition of dictionary of words from the dictionary, but there are some differences. First, there's no need to mask anything, right? BERT when fine-tuning, we don't mask anything, definitely. Secondly, because we know, okay, for this word COVID, it corresponds to this definition, there's no use to further just putting in more negative information. So there's no negative definition here. And finally, we only allow attention between this word to this definition because we know that, okay, this word, the definition of this word is here. So we want to provide the most and information and most accurate information to the inference. So this is during fine-tuning. Let's look at the experiments. We conduct the.
Sorry, can I ask a question before you move on? How do you choose these additional words? So you said for COVID, you choose like epidemic and COVID. So it is a automatic method. You pick some random words in the original description, or how do you do that?
That's a good question. Actually, we prioritize words that appear less in the pre-training corpus. That's those words are exactly words that require more information from the dictionary. If there are common words, say love or university, the language model can understand it pretty good. Yeah.
But and then how do you assign the labels if they are correct or not? I mean, is this a manual task, or that's what I'm trying to understand. Can you automatically generate this training data, or you're manually generating it?
Oh, you mean why do we select COVID and epidemic and not other words here?
Yeah. So why do you select COVID and epidemic, and also how do you assign the?
Oh, so
if it's correct or wrong, and is that a manual process, or you have some automatic procedure? to add this additional training?
Yeah, so basically we rank all the words according to their frequency in the pre-training data. And then we set the threshold. So for those words like below that threshold, and also definitely you should have a definition in the dictionary, then we put it here. Right.
Yeah, I think I also have a question which is relevant to Mr. Lewis's question. So how do you do word sense disambiguation?
Oh, that's yeah, that's a very good question. Yeah, I believe this can, although we don't do it in this work, this is an open question, right? For I think some words they have multiple senses, so we can have another module in the pipeline to first determine.
So that means at this moment you are using the dominant sense.
Yeah, we just use the first definition of that in the dictionary. Yeah, and that also applies to the Common Sense Q&A work. Yeah, that's a good question. So for the pre-training, we just follow the BERT pre-training using the same pre-training data, and then we choose downstream tasks for different types, and we introduce them. The first task is about novel words and new words learning, and all of the test data looks like, okay, given a word, then it's the opposite of something. So it's more like say a GRE test about your understanding of a vocabulary. Although here they specifically test more like real words. So here compared to BERT, we notice that for those real words, meaning they appear less than 10 times in the pre-training data, actually we perform the improvement is most dominant here, because that in that case, dictionary can help a lot. And for frequent word, actually, the performance don't drop. So overall, we still have better results than a BERT. So this agrees with our previous hypothesis that dictionary should help with those relatively new words, real words. And that actually is common, right? Like before 2019, there was no word called COVID, but now it's pretty frequent. So that's also like a temporal relationship there. Then secondly, we test this, our method on the general NLU task, which is a glue benchmark. So in glue benchmark, they didn't say, okay, all of the most of the words are novel. It's just general. So it shows that, okay, even on this general task, dictionary can still help, right? So that's the main observation here. And finally, we tried this method on another case where new words are more common, which is domain shift, like domain transfer. We tried the DAPT or TAPT, it's called a domain adaptation, task adaptation on the DSP dataset, which has 4 domains: biology, computer science, news, and reviews. So it has a lot of new terminologies. And here again, our work actually outperforms the DAPT and definitely outperforms the baseline of like non-DAPT, just directly fine-tuning. So it proves that in new domains or tasks with more new words, the definitions will definitely help. And on like general NLU tasks, it also helps, although the magnitude is smaller. Okay, so that's the second piece of work on dictionary. Finally, let's look at our another work, which is called knowledge and language co-pretraining. So we know that language model pre-training is quite successful, and it has been used in many cases. But in custom scenarios, like we meet that a lot, encounter that like maybe once a month in industry. Right? That's pretty common. We have new entities and new relations that a model was never exposed before. Some people may say, okay, you can use customer text to like adapt. You can continue pre-training using BERT, MLM on the custom text. But the thing is, customers usually do not have those large quantity of text. Not like, although there are a few like of them that can afford to have a large text corpus, but not all of them are like that. And also, as I've said in the beginning of the talk, obtaining knowledge from text is inefficient, right? Especially in these downstream tasks. So we want to solve this problem. But let us first revisit how we like integrate knowledge into language models. Here's a typical setting we have done before. Given the input text, the language model has this input. Then we try to use NER to locate the knowledge graph nodes corresponding to these entities. And then say we'll compute the graph neural network embeddings and then append or add that to here. So that is called knowledge-aware entity embedding. Like we can fuse that information from the left side to the right side. But we noticed that on the other direction is also valid, but few people have looked at. For instance, if you look at here, this graph says, okay, Office is a software in Windows 10. It's actually WIN 10. But this WIN 10 is actually a very novel word. And usually knowledge graph is just constructed in a way that, okay, the only information about a node is its name. It lacks context. It does have a lot of structural information, but if a model comes to comprehend it, what is Win 10? Is it an animal or fruit, right? So it doesn't know. In this case, the language model can come to help. If we can provide each knowledge graph node with a definition, say Windows 10, we can have a sentence describing it. Say it's a software, it's an operating system developed by Microsoft, then we know more about this node, right? Thus, we argue that the language model can be used to compute the contextual information for this node. And how can we use it? One way that we tried is we use the contextual embedding of Win 10 in that definition sentence as the 0th layer embedding for Win 10. And then starting from that 0th layer, the graph neural network can compute the first layer, second layer, third layer, and so on. But here, because of the language model, the 0th layer has much more contextual information about each individual node instead of just using its name. We argue that if we do this direction and also this direction, both sides will benefit and they will benefit each other better. But there's one problem in this design. I'm not sure whether you have noticed it, is that the whole architecture is cyclic. So actually, if you do this in a naive way, you will not be able to do one gradient descent. The reason being, okay, I want to compute the language model embedding from here. So let's first get the knowledge graph embedding. But to get this, we need to get the contextual embedding using this language model to get embedding for the definition sentence. But for that, it may contain even more entities and it will come back to the knowledge graph. So it's an endless cycle. We propose to break this cycle with a special design, which is here. We break that language model into two parts. The lower half layers called transformer 1 and the top half is called transformer 2. When we try to compute the definition sentences embedding, we use transformer 1. And then we get the graph neural network embedding, but that is only applied to transformer 2. So transformer 2 gets information from both transformer 1 and the graph neural network. In this way, each part still gets information from each other, and as you can see, there's no cycle anymore, right? Here is the whole process. We have the input, say, okay, Windows 10 is operating system that can do something, right? And then we try to look for its definition for certain entities appearing in it, like Win 10. And then for each one, we associate it with a description text. The reason we can find this description text is because during pre-training, we use Wikidata as the knowledge graph. And the first paragraph in the corresponding node for the Wikipedia page as the description, right? And then we can get the embedding of Windows 10 here using this language model, the transformer 1 to be exact, to get the embedding of Windows 10. And then we take the average of these two embeddings as the starting embedding for Win 10. And then using this to get the, like say, the third layer GNA embedding as the final entity embedding and fuse that into transformer 2. Yeah, that's close the whole computation cycle. For pre-training, we have learning objectives for both the language model part, which is includes the canonical MLM and also mask entity prediction. Basically, we prioritize masking concepts. For the graph neural network part, we mask the link relation and also the masked entity prediction. So it's basically self-learning. I want to emphasize that although during pre-training we use Wikipedia and Wikidata, the whole architecture is not confined to that specific knowledge source. Instead, the model learns how to get information from any knowledge source. Thus, during fine-tuning, during customer scenarios, can completely replace the knowledge graph with a new one. Like this is Google product, right? It can contain like weird names like XYZ, ABC, as long as there are description tags associated with each node. This is not a big requirement for customers, because if they give a knowledge graph, they should explain those terminologies, right? And because the model is already adapted to learning from any knowledge graph sources to assist its own language modeling, this whole pipeline still works, and it actually works well according to the experiments. So here we'll conduct experiments first on few-rail. It's a few-shot relation classification. So after training, in the test, they always provide supporting set and test instance. Supporting set provides with a certain number of new relations not seen during the training. And then for each new relation, they provide several examples. Here they give 2 examples, so it's called two-shot. And then immediately after the model sees this, it should give its prediction on the relation between this word and this phrase in the new test instance, given these 3 new relations. So this is called 3-way, because this is 3-way choice, and two-shot, because every new relation is associated with 2 examples. Then we test it on the canonical 5-way one-shot, 5-way 5-shot, and 10-way one-shot, and notice that our method can significantly improve the result compared to say the BERT base, which we start with without any without any co-pretraining of knowledge and language model. For the second task, we demonstrate the capability of the architecture using new knowledge. So this is called this data set is called MetaQA. It's a question answering task for movie knowledge, like what are the genres for movies written by a certain script writer. And here, this knowledge graph is a new one. They provide this. So for this task, we just dump the wiki data that we used as KG during pre-training and directly use this, and then search for the definition of these words. So the model quickly adapts to this scenario, right? And for this experiment, we show that in different settings, actually, our performance is much higher. So notice that this actually, I should say that our base is actually Roberta base. Yeah, someone just asked in the QA. So our base is actually Roberta base, but with the co-pretraining with KG. So this is the Roberta base alone without any KG in the training. This is, we use Roberta base and the graph neural network, but they were not co-pretrained during pre-training. They are just, the GCN is just randomly initialized during fine-tuning. So it turns out that if we do that during pre-training and each part helps each other, the performance is much better.
I think there are 2 quick questions from the chat. One question is, you already saw that, which transformer architecture is used in our base?
It's a Roberta base. Yeah.
Okay. And the other question from Joe is, for the few-shot downstream task, do you also perform gradient updates with limited examples for the task?
Yes. Yeah, because this model is not like a prompt-based model. So it's, yeah, there's some gradient updates for that. So this is according to the setting of that task. Okay, so to summarize the various 4 tasks that I have talked about in this talk, they are very different by nature. However, if we look at them, our method can all be categorized as like some application of the 3 steps: grounding, representation, and fusing. So let's look at them. For the CommonsenseQA, we use the KG or ConceptNet as knowledge source, and also Wiktionary, the dictionary, and training data. For ConceptNet, fortunately, they give us the knowledge grounding for free. For Wiktionary, we use tokenize and string matching as grounding method. And training data with BM25 or information retrieval. The representation is just textual descriptions, and fusing is just appending. For multilingual CommonsenseQA, it's like ConceptNet and Wiktionary are similar. The new things are corpus, where we use IR, and GPT-3, where we use model inference to elicit the knowledge. And then again, it's textual knowledge, so append. For dictionary, LM, the DictBERT, which just use Wiktionary as knowledge source. Grounding is like tokenize and appending. The last one, the co-pretraining of KG and text, the knowledge source is the knowledge graph Wikidata, and the grounding is by NER. And the representation is using GNN embeddings, and the fusing is adding that embedding into the word embedding. So although they're very different, as long as we follow those 3 steps, we got like improvements of various scales on these tasks. And if you are interested in learning more of our work in this field, we do have more, but because of the time constraint, I cannot talk all of them. We have conduct a tutorial on knowledge augmented methods for NLP in this year's ACL. And also we have a workshop just accepted on the same topic next year in AAAI. So if you're interested, feel free to participate. And finally, we have a survey paper that comprehensively look at the knowledge enhanced methods for NLG, which is published in ACM Computing Surveys. Before I end this talk, I want to talk about a few future directions that we're working on, and there are also open questions, so welcome any like ideas or further collaborations on this. First topic is, although we applied knowledge predominantly on NLP, we believe that it should also benefit other modalities learning, like vision and speech. The reason that knowledge is now more used in NLP field is primarily because knowledge is usually stored in text format, like KG, free text, so on. So to leverage knowledge in other modalities, I would propose like 2 ways. Either we can convert other modalities input into text and then get the knowledge from text. Say for a picture, I first use image captioning to get its description, and then we retrieve knowledge based on that text. So we know how to do that because it's an NLP problem again. Or we can store the knowledge into the corresponding modalities. Like instead of like saving this a knowledge graph where everything is text, say there's a node for cat, there's a node for dog, and it's just described by CAT, DOG, we represent each node by a number of pictures or some sounds of the cat and dog. And then given the multimodality input, we can do retrieval in that space, like do the image similarity search or audio similarity search, and then get information from that. Right? Second topic is how to unify the representation for knowledge and text. As we know, especially for knowledge graph, they are computed most efficiently by GNN, but text is computed by transformer. They are very different in nature, and we actually have to do a lot of work in how to like uniform their embedding distribution to make it work better. Because sometimes their scale just are different by a lot, so directly adding actually would hurt. Can we use a single architecture to optimize to handle knowledge graph and also text? That's an open question. Some people propose this graph transformer, but graph transformer is not actually used for text. So can we just convert everything into text? That's one way. Or like for text, we can convert it into knowledge into graph format. So that we can use one model to conduct end-to-end optimization. That's an open question. Okay, finally, I want to conduct a brief introduction to our team. So currently, I lead this knowledge and language team in cognitive services. The whole org is headed by Chenguang. And so currently, our team has 10 people, including me. There are PhDs, and we have actually 3 more coming in a few weeks. And we do have USC alumni, and we also have people from Stanford, CMU, etc. So our group conducts both originated research, conduct publication, and also push our technologies into product just inside our cognitive services primarily. And for publications, actually, we have a strong publication record in like recent conferences. Like we have 9 papers in ACL and 2 papers like this week in NIPS. We also get human parities in a number of competitions and also first places in leaderboards. And then not only do we publish, but we also try to put what we publish into real product and to impact millions of people's experience. And we are now actively hiring full-time researchers and also interns and research engineers. And I already put some information of that in my LinkedIn. So if you are interested, feel free to check it out or contact me at this email address. Again, thanks Muhao very much for inviting me for this talk. And thank you very much for your time. And I'm happy to take questions. Thank you.
Yeah, thanks, Chenguang. This is really a great talk and also very interesting works. Also, as I always say, you have a great team.
You also have a great team.
Yeah. I guess any more questions from the audience? Yeah. Yeah, I think the idea of using the uniform architecture, transformer architecture to capture both the graph and the text modality is definitely very interesting, and also somewhat that's relevant to how people jointly capture tables and text, because tables are considered semi-structures. The graph is just a more complicated structure, but over there, recent works, including some of ours, will prune the attention flow to become a structural attention flow. That's probably one way, I guess.
Mm-hmm. Yeah, that's a great suggestion. We actually do have work on using knowledge from both text, say Wikipedia text, and tables from Wikipedia. And so I remember there we just convert tables into text following some approaches and row-wise. That
works. Linearization, yeah, but that loses the structure. So in that case, yeah, you need to somehow prune the attention flow to preserve the structure.
Exactly.
Yeah. Okay, I see this. Okay, would you be sharing the recorded video? Definitely, of course. Yeah. Also, another interesting thing I think is relevant to the dictionary part of your work is that over there, it definitely makes a lot of sense to use dictionary or any kind of lexicographical knowledge to represent rare concepts. But that's on the feature side, right? We are also very interested in using a similar kind of method to, for example, you can think about using dictionary to jumpstart the decision space. So if they are rare or unseen decisions, the dictionary provides a semantic representation for that.
I see. So you mean for decision-making tasks, right?
Yeah.
The
simplest way is just to use the dictionary to represent labels, right?
Oh, that's a new stuff. Ah, I see. It's interesting. So I think although the model learns a lot, it's usually just look at the free text. So, but dictionary is a highly condensed information, highly authoritative from linguists, right? And so we think that's why we look at it. And I personally use the dictionaries in my daily life, and I believe it should also help with models for various tasks, including decision making. So yeah, we can have a try on that. According to our experiences, it does not hurt to add information. But one caveat is when we append a specific information as text, append this knowledge, do not make it too long. Otherwise, it will overwhelm the input. Because otherwise, the model would see 90% of the knowledge, but only 10% of the input. And we sometimes do some like truncation there.
Yeah. Okay.
I have one quick question if there's time.
Yes.
I was wondering, in one of your tasks, you were saying you were using NER for the grounding. And I was curious how the noise of that process would affect the quality of the model that you learn.
Yeah, that's a good question, because we just use it and like do it once. We don't know what, like, if we use a even better NER, would that be better? But I think in general it should help, right? This is, I would say this is we depend on like better NER tools, so we can benefit from that. So definitely, if a crappy NER which is 50% wrong, definitely I don't think that would help a lot.
Okay. All right.
Okay, I guess we are past 12 already, but we have already asked a lot of questions, and I look forward to the continuing discussion with you in one-on-one meeting. But thanks once again for this really interesting and great works. Yeah.
Thank you very much, Mohan, and thank you everyone for your time.
Thanks. Okay.